Hello, my name is Matthew Abate, and today I'm going to be speaking about some of the work that myself and my collaborator Corbin Klett have been conducting in the Georgia Tech Facts Lab and the Georgia Tech Decision and Controls Lab. The title of my presentation today is Pointwise and Time Analysis in Non-Quadratic Lyapunov Functions for Linear Time Varying Systems, and this work was advised by Dr. Sam Coogan and Dr. Eric Ferrone. So we'll begin by looking at the linear time-invariant system given as equation 1, where x is the state, u is a scalar control input, and y is a scalar system output. And in this work, we're particularly interested in studying two things: the impulse response of the system, given as equation 2, and the step response of the system, given as equation 3. All right, in the deterministic setting, it's relatively easy to compute via simulation these terms, h of t and s of t. However, when there are time-varying parameters included, as in those we'll consider later, it can be difficult to come up with bounds on h of t or s of t using methods other than time domain simulations, which can be exhaustive and computationally intense when, say, the system dimension is large. All right, so in this work, we're going to try to present some efficient tools for estimating and bounding these terms. And we'll begin with an approach for over-approximating h of t, or computing a norm bound on h of t that relies on quadratic Lyapunov functions. All right, so this is a canonical result. Quadratic Lyapunov function for the system x dot is equal to ax is given by vx is equal to x transpose px, where p is positive definite and satisfies the relation given on equation 4. All right, and when you have a quadratic Lyapunov function for your linear system, then you can compute using equation 5 a global norm bound on the impulse response of the system. Okay, and we'll demonstrate this procedure on the next slide. Okay, so here we're considering the linear time-invariant system given as equation 6, and we're going to apply the procedure from the previous slide using a p matrix as a scalar multiple of the identity, which is a Lyapunov, which leads to a Lyapunov function for the uncontrolled dynamics. And when we apply this procedure, we get a global norm bound on h. So if we look at the time domain plot shown on the lower right, the blue trajectory, this is the impulse response of the system, and the red lines mark the norm bound achieved using this procedure. All right, and to give a little bit of intuition here as to what's going on under the hood, we can look at a phase plane representation of the impulse response. What's happening is that the system is asymptotically stable. So when you start at the blue dot, this is the beginning of the impulse response, you're going to converge towards the origin, but we have this Lyapunov function which gives you invariant sublevel sets. So we know that the impulse response must remain inside of a circle that touches the initial system condition. Okay, and then finding the intersection of this circular sublevel set with the C vector, we are able to attain a norm bound on H. All right, and what we see here is that this method is good. It gives us a norm bound on H, but it has two flaws. So first off, there's a bit of conservatism. You can see this in both plots. And second, it's a global norm bound. It's static. It doesn't change with time. So if I was to say, what is a norm bound on H starting at 12 seconds, you would be stuck with the initial norm bound, which in this case is too conservative to really tell you anything useful about the system. All right, so in this work we are going to address these conservatism problems, and we're going to use a related hierarchy of linear time-invariant systems in order to deduce better norm bounds on the impulse and step response of your system. All right, and in particular, we're going to consider this infinite hierarchy of linear time-invariant systems given as equation 7. For some intuition here, these come from vectorized versions of the Lyapunov differential equation of the initial system. And an important point here is that if you take one of the systems in the hierarchy and you compute a quadratic Lyapunov function for it, this will tell you a higher order homogeneous polynomial Lyapunov function for your initial system dynamics. All right, and in this work, what we're going to do is we're going to take quadratic Lyapunov functions for these higher order systems. We're going to convert them into higher order homogeneous polynomial Lyapunov functions for your initial system, and then we're going to use these Lyapunov functions to construct tighter bounds on the impulse and step response for LTI systems, and we're also going to construct time-varying bounds using this technique. So this rectifies the two problems identified on the previous slide. So we'll begin by showing how the impulse response for linear time-invariant systems is bounded using these higher-order homogeneous polynomial Lyapunov functions. So say you have a quadratic Lyapunov function for the ith level system in your hierarchy, then you can use equation 10 to construct a bound on the impulse response for your initial LTI system. Okay, and we're going to demonstrate that on the next slide, but before we do, there's just a remark here to note, which is that you can actually formulate the search for the tightest possible bound using this approach as a semi-definite program. All right, so what we're going to do is we're going to solve the optimization problem given as equation 11. This gives us a very specific P matrix, which is a quadratic Lyapunov function for a higher order system. And then we're going to take that P matrix, plug it into 10, and this is going to give us a norm bound on the impulse response for our initial system. Okay, so on this slide we're presenting a second example, and we're considering the linear time-invariant system with parameters given in equation 12. And this is actually a very specific and important linear time-varying system. It's sometimes called the stiff linear system. It is based around this parameter m, and it is known that as m increases, it goes to infinity, the bound on the impulse response that is attainable using quadratic Lyapunov functions also goes to infinity. So your system is always stable, but you can't use quadratic Lyapunov functions alone to compute a global bound on the impulse response. However, what we can do is we can apply this approach shown on the previous slide, an iterative approach to construct, say, not only quadratic Lyapunov functions, but fourth order and 10th order homogeneous polynomial Lyapunov functions for this stiff system, and then use an analogous technique to compute bounds on the impulse response. So this is shown on the lower left in the phase plane and on the lower right in the time domain. So note that as the order of the Lyapunov function increases, the bounds attained using our theorem increase in fidelity and give you better approximations of the true maximum impulse response. Okay, we apply this to the step response for LTI systems as well. So when you have a matrix P which defines a homogeneous polynomial Lyapunov function for your initial system at some high order, you can use equation 13 to compute global bounds on the step response of your LTI system. And you can also similarly formulate a semi-definite program using equation 14 to search for this matrix P that gives you the tightest bound in your step response. So this is a directly analogous result, and we'll demonstrate it next. So in this example, in equation 15, we're considering now a three-dimensional LTI system, and we're going to compute norm bounds on the step response using the result on the previous slide, using second order and sixth order homogeneous polynomial Lyapunov functions. And we also here provide a technique for bounding the tail of the step response in terms of a norm bound. So what you can see in the figure is that for the first 4 seconds we're computing a bound using say the initial result, and then this bound is recomputed at time 4 to give you added fidelity as to where your step response lives. All right, so for the remainder of this talk, we're going to be talking about linear time-varying systems. So a linear time-varying system is given as equation 16, where we assume that the A matrix is now time-varying and involves in some bounded convex set of A matrices. And in this case, the impulse response is described parametrically by a solution to equations 18. Okay, so if A changes, if you have a new time-varying A matrix, then the impulse response of the system actually changes. But what we are going to do is provide a method for computing global norm bounds on H in this case as well. However, due to time constraints, I'm just going to sort of skip to the example and show you what you can achieve if you use our technique. So in this case, we're considering the linear time-varying system given as equation 19. And in the figures on the bottom of this slide, plotted in blue, are possible impulse responses depending on the time-varying nature of A. So so you have 3 different time-varying A matrices. This leads to the 3 blue responses shown on the bottom of this slide. Okay, In our work, we present a few techniques for computing bounds on the impulse response in this setting. The first technique is demonstrated on the left of this slide, and this involves exponentially growing or decaying bounds on the impulse response. So these are all from 12th order homogeneous polynomial Lyapunov functions for the system 19. The orange bounds are growing. They're exponentially growing bounds, whereas the green bounds are exponentially decaying. Okay, and when you apply a result with a growth parameter equal to 0, you attain this initial result, which is just a static bound on the impulse response. So this is shown in red. All right, we also present a method for computing envelope bounds on the system's impulse and step responses, as shown on the right. So in this case, the red and green lines describe envelope bounds from 2nd and 6th order homogeneous polynomial Lyapunov functions. And then the last thing we do is we combine these two ideas, exponential growth and decay, with envelope bounds to compute envelope bounds that grow or decay with time, as shown on the bottom. I don't have time here to fully get in to all the results, but I do recommend our publication to the interested reader, because I think the math is intuitive, simple, and easy to understand. All right, so with that, I'll just wrap up. In this work, we show how a related hierarchy of Lyapunov differential equations is used to compute bounds on the impulse and step response of linear time-varying systems, and we actually present several techniques for attaining such bounds. Thank you for listening. My name is Matthew Abate, and I've included my contact information on the bottom of this slide.